Hi there and welcome back. Let us develop a dynamic model for this process illustrated, which is a stir tank heating process. Assumptions that we can make is that in the tank we have a perfectly mixed solution. The exit temperature is T and the entering temperature is Ti. We can assume constant volume because the inlet and the outlet flow rate are equal. Also that density and the heat capacity C are assumed to be constant. Let's also neglect any heat losses. Key box, we have U being the internal energy, H being the enthalpy, W being the mass flow rate, Q it's the rate of heat transferred to the system, and anything delta or D is basically change of. Conservation of energy balance, we can say that rate of energy accumulated is equals to the rate of energy entering, subtracting the rate of energy exiting, with the rate of energy generated, subtracting the rate of energy converted in the system. Assume that there's nothing consumed and generated, we'll be left with accumulated equated to rate of energy in, subtracting the rate of energy out. We can therefore substitute variables for the energy balance and we can represent the rate of energy accumulated as du over dt. Equated to the rate of energy entering, we can say Wi and the temperature entering, subtracting the W, which is the mass flow rate, the enthalpy out, and T plus heat. This is very common in thermodynamics. For a pure liquid at moderate pressure, the internal energy is approximately equal to the enthalpy. So we can say U is approximately equal to H, and we can say the specific heat capacity at constant temperature delta T will be equal to dU. We can also say that specific internal energy is equals to mass multiplied by the internal energy, and mass can also further be derived as density multiplied by volume. So everything can be written as density, volume, and internal energy. For enthalpy, we can say that it's equals to specific heat capacity at constant pressure, and with the temperature minusing the temperature reference, we can say temperature reference is 0. We can therefore now go back to the energy equation derived and substitute everything. We managed to obtain the specific internal energy to be represented as density, volume, heat capacity, delta T over change in time, and we can also substitute the enthalpy plus the heat transferred to the system. I really hope this makes sense. For part 2, we are going to discuss the types of controls. This includes feed forward and feedback for this very same system. Thanks for watching.